Hi everyone, welcome to this video where I'm going to discuss about the data encryption standard in detail, how the algorithm works. We already studied about the simplified DES, which is a version where you can understand the operations, how they are performed, how the algorithm works with small amounts of data. Let us check the original algorithm in this video. As you already know, the DES is a symmetric key encryption algorithm, which is used for encrypting the electronic data. Though it is no longer used today, it is very highly influential in the advancement of modern cryptography. It was the first standard that was published by the US government to be used for all different kinds of data. DES was approved as a federal standard in November 1976 and also published on 15th January 1977 as the FIPS Publication 46. FIPS stands for Federal Information Processing Standard, and the Publication 46, which is authorized for use on all unclassified data. If you want to know about the history of DES, it dates back to 1972, where a National Bureau of Standards study related to the US government's computer security identified a need for a government-wide standardized encryption algorithm, which can be used for unclassified and sensitive information. There, the NIST has requested proposals to come up with this particularized national symmetric key encryption scheme. There, IBM has submitted its own proposal of an algorithm they are currently using, which is known to be LUCIFER. Though they made some minor changes to it before submission, LUCIFER was widely accepted and LUCIFER has been standardized as data encryption standard. You can see that it was the first encryption algorithm that was approved by the US government for public disclosure. This move ensured it was quickly adopted by industries such as financial services that needed strong encryption. Because it is simple, DES was also used in a variety of embedded systems, including smart cards, SIM cards, modems, routers, and also set-top boxes. In a way, it is an implementation of the Faisal cipher structure. Faisal cipher structure forms a blueprint for many of the symmetric encryption algorithms where data, the plain text data is divided into blocks of equal halves, and whatever operations we are performing, they are being performed on the different blocks. So it uses a 16-round Faisal structure with the plain text processed in 64-bit block sizes. Though the key length is 64 bits, the effective key length of DES is 56 bits only, since 8 bits of the 64 bits are not used by the encryption algorithm. We will check out where the 64 bits are, how these 56 bits are used, and all these things in the subsequent slides. This is the overall structure of data encryption standard. It also uses the two basic techniques of cryptography called as confusion and diffusion. So these two are the desirable properties of operation for a symmetric cipher as identified by Claude Shannon in his 1945 paper. To understand, the property of confusion hides the relationship between the ciphertext and the key. It means that each bit of the ciphertext should be dependent on several parts of the key, completely obscuring the connections between those both. So the ciphertext and the key, the connection between them should be obscured. It makes cryptanalysis much more difficult. The second property, called as diffusion, it hides the statistical relationship between the plain text and the ciphertext. In other words, if there is a little bit of change in the plain text, that means if you change even one bit in the plain text, there must be considerably huge change in the ciphertext. Any patterns of redundant bits or observable patterns in the plain text should not be apparent in the ciphertext for an attacker. So these two are very important properties, and DES actually uses these two techniques to implement encryption. You can see that at the simplest level, diffusion is achieved through numerous permutations, and confusion is achieved through the exclusive OR operation and the S boxes. This entire structure is also called as an SP network, substitution permutation network. If you see, this is the original encryption part, or how the DES works, and all of this is your key generation part. There are two parts in this. This is the key generation part. Now let me explain to you how this works briefly, and then we can go a little bit in depth of how the structure is and what is done in each round. In data encryption standard, there are 16 identical stages of processing termed rounds. You can see that round 1, round 2, I have clearly mentioned there are until round 16. So DES implements the encryption, or DES algorithm works in 16 rounds. These are identical, where the functionality inside the each round is similar. But the only difference being each round uses a 48-bit unique subkey which is generated from the original 64-bit key issued by the user. So once we give the 64-bit key, there is a key generation algorithm which is able to generate 48-bit unique subkeys for each one of these 16 rounds. So for each one of these 16 rounds, we get 16 unique 48-bit keys. Remember, 48-bit keys for each round, okay, which are generated from the main key. So if you change the main key, once again, all of these will be different. There is also an initial and final permutation termed IP and inverse IP, which are inverses. You can see that once you take the plain text, this is a block cipher. As I told you, block cipher implements or works on the plain text in blocks of fixed sizes. It might be 64, it might be 128, it might be 192, whatever it is. The block size is fixed. So DES also starts working on 64-bit blocks. Once you issue the 64-bit block, the first operation that it performs is something called as initial permutation. And towards the end, after all your 16 rounds of processing is done, followed by a 32-bit swap of the two halves, and towards the end, there is another permutation called as inverse IP. These both are inverses to each other. Before the main rounds, the block is divided into two 32-bit halves and processed alternatively, similar to Faisal cipher structure, which means that once you take the 64-bit plain text, you divide it into two halves, left and right. So 32 bits each, and you start processing on each half of this block. That means 32 bits we do, and once again we perform the operations on the 32 bits. We continue the same structure till the end, the same kind of operations. So the DES decryption and encryption are very similar processes. The only difference is that the subkeys are applied in the reverse order while decrypting. We have the same rounds again, but the only difference is when we use the first subkey in round 1 here, during decryption, we use the 16th subkey in round 1. That is the only primary difference between DES encryption and decryption. That is also one contributing factors which made DES very popular. You need not have two algorithms. The same algorithm can be implemented for encryption as well as decryption, with the only difference being application of the subkeys or the order of application of your subkeys. This is how a usual round looks like in a DES. As I told you, the 64-bit permitted input passes through 16 iterations, which we call them as rounds, producing an intermediate 64-bit value at the conclusion of each iteration. Means for every round after round 1, we have a 64-bit output, and this 64-bit output is passed on to round 2. And once again, it is after the round 2 is completed, we have another 64-bit intermediate output. This is passed on to round 3, which is carried on till round 16. So what happens in this particular round? You can see once again, this part tells you the operations that are performed in each round, whereas this part is going to tell you how the key is being generated. So let me explain the round key first, or the round structure first, then we will pass on to how the keys are being produced in the later stages. The 64-bit, as I told you, is now divided into two halves. Okay, so the first 64-bit key or the 64-bit plain text is divided into equal blocks or equal sized blocks of 32-bit. We call it as the left block and the right block, and they are separate as labeled left and right. The overall processing at each iteration is given by the following step, which form one round in a substitution permutation network. So what is happening here? You can see that the first left side of the 32 or the left side of your plain text is kept as it is, and it is only used towards the end. You can see the left of, if you want to understand this, let me assume that this is round 2 here. This is round 2, and after all the processing in round 2, you go to round 3. So how do you write what is happening in round 2? You can say that after round 2, L3 for the round is R2. That means you can see this. For the third round, the left hand side input for the third round is nothing but the right hand side input of round 2. That is what I have written here. And what about R3? That is what is the right hand input for round 3, which is nothing but you have, first let me define this function and then we will go with this. A function of or a function f which is being defined on the right hand side input and the sub key ki. Ki is 48 bits and this is 48 bits. So sir, but you told me it is 32 bits. Then how come you got it as 48 here? Because you have a 48 bit sub key. That is the reason we have a function which contains different operations again, which we call it as expansion permutation ebox, which increases the 32-bit input to 48 bits, which expands the 32-bit input to 48 bits, and then we perform an exclusive OR. You can see here, we perform an exclusive OR with the subkey ki for each round, and then this is the expansion permutation, and then we pass this on to a substitution S box. This is the S box here. And finally, we have another permutation which reorders these 32 bits into one particular format. This is this. This is the output of your function. Once we get 32 bits, these 32 bits are performed an exclusive OR operation with the left hand side bit. This is how it carries on. So L2 exclusive OR with f of R2 comma K2. This is how you write for a round 3. Similarly, you can write for any different round from round 1 to round 16. This is how you perform the operations. So, sir, what are these operations? What happens internally? If you remember my simplified DES video, we should be able to understand because we performed this on smaller bits of data on the 10-bit plain text as well. I have clearly shown you how the expansion takes place and we performed a couple of examples also. Okay, if required, you can please go back to that video, watch it once before trying to understand each and every operation of the original DES algorithm. The left hand output of an iteration Li is equal to the right hand input to that iteration. That is what I told you. The right hand output Ri is exclusive OR of Li minus 1 and a complex function f of Ri minus 1 and Ki. To understand this, let me show you. This is the initial permutation. So the first 64 bits of your plain text or the entire 64-bit block of your plain text is rearranged in this order. This is the order of rearrangement. The 64 bits are rearranged, and towards the end I also told you that there is an inverse IP. Once again, the bits after your processing of 16 rounds is done and you perform a swap of the 32 bits, you perform this IP inverse. You rearrange the bits once again in this order. You can see this is the expansion permutation which takes your 32-bit half and expands it to 48-bit. This 48-bit is then exclusively ORed with your round key. After your round key is done, you pass it on to an S box which will reduce the 48 bits to 32 bits again. And that is the reason we have total of 8 S boxes that we are using in your DES algorithm. And once the S boxes reduce the 48-bit to 32-bit, we perform this permutation function P, which will rearrange the 32 bits into this particular order. These are all fixed. Okay, these are all fixed. So remember that for your initial permutation, you take the 64-bit plain text block, you rearrange the bits into this particular order. After that, you process on with your round functions, round 1, round 2, so on till round 16. The output of round 16, which is once again 64 bits in length, you swap it. So the left becomes right and right becomes left. And once you get those 64 bits after the 32-bit swap, you perform the inverse initial permutation in this particular order. So what happens in that round function and what happens in that complex function is that you have an expansion permutation which accepts the 32-bit input, expands it to 48-bit, then followed by the exclusive OR with the round key, which is once again 48-bit in length, and then followed by an S box, substitution box, where there we have an 8 S boxes, which will take 48 bits and bring them back to 32 bits. We have 8 S boxes, which will accept 6-bit input. I'll show you, which is a total of 48 bits. And similarly, all the 8 S boxes produce 4 bits as output, which is nothing but 32 bits. So we reduce 48 bits to 32 bits. This 32 bits and are then subjected to the permutation function P, and they are rearranged in this particular order and then passed on to the next function. Okay, so you can see this is how the round function works. The heart of this cipher is the DES function F. The DES function applies a 48-bit key to the rightmost 32 bits to produce a 32-bit output. So this is my round key, which is 48 bits in length, and this is the 32 bits which I got it from the right hand side data. Now, in order to perform an exclusive OR, I need 48 bits also, isn't it? So that these 32 bits are now subjected to something called as an E box or expansion permutation box. In this E box, these 32 bits are expanded to become 48 bits. These 48 bits are now exclusive ORed with the round key. So you get an output of once again 48 bits. These 48 bits are now issued as an input to the S boxes. A total of 8 S boxes are present here: S1, S2, S3, S4, S5, S6, S7, and S8. There are 8 S boxes. So these 48 bits are issued as 6-bit, 6-bit, 6-bit. So each one of these S box will receive a 6-bit input, and then each one of these will produce a 4-bit output. So altogether 8 S boxes with producing 4-bit output gives me 32 bits. These 32 bits are now issued as an input to the P box or permutation box, which will rearrange these 32 bits in some particular order. That's it. And then it will issue the 32-bit output, which will be then performed an exclusive OR with the left hand side, as you see in the original structure or the original round structure. So the expansion permutation box or the P box, since the right input is only 32 bits in length and the round key is 48 bits, we need to expand it. I have shown you how we expand this, isn't it? So this is how you expand it. The 32 bits are taken here and you write them in this particular order, which gives me, so this is 8-bit, this box is 8-bit. So 8 bits plus 8 bits, 16, and the original 32 bits are here, which gives me a total of 48 bits. Once again, I request you to refer to SDS for a better understanding. And then followed by the exclusive operation with the round key, which is 48 bits in length. Then you follow it up with the S boxes. Each S box takes a 6-bit input and produces 4-bit output. I will show you how it is being done also. And then followed by the permutation function, which will rearrange these 32 bits in this particular order. The particular order in which the 32 bits are arranged is given here. Okay. Now, these are the 8 S boxes, as I told you. There are 8 S boxes are used for the reduction of bits from 48 to 32 bits. And for each 6-bit input, a 4-bit output is produced, which results in the reduction. You can see this. Now let me assume I'll take a small example. These are the 8 S boxes which are designed for DES. These are also once again fixed and you cannot tinker with them. Okay. So for an input which is 6 bits in length, 0, 1, 1, 0, 0, 1. Let me assume that if I am giving this input to S1, okay, for S1 or S box 1, what you do is you take 0, 1, 1, 0, 0, 1. The first bit and the last bit, these two form the row, and the remaining 4 bits in between form the column. Okay, so 0, 1 will be the row here. So what is 0, 1? It's 1. And the middle one, 1, 1, 0, 0 is number 12. 1, 1, 0, 0 is 12. 12 is here, 9, A, B, C. This is 12. And if you take it here, you get the output as 9, which can be written as 1, 0, 0, 1. So 6 bits input. The first bit and the last bit is selected to become the row. And the remaining 4 bits in between are selected to be the column. See where the two map. Check what is the value in that particular table, and that particular value is written in 4 bits. So 6 bits input, 4-bit output. Altogether 8 S boxes, 8 6 are 48 bits as input, 8 4s are 32 bits as output. So we get the reduction of 48 bits to 32 bits in DES. This is how an S box works. So the design of these S boxes, why we are only writing these values, are kept a secret. The design is not made public, how this is being done, and there are many theories and some conspiracy theories also on why they kept this S boxes, design of S boxes away from the public keys for NSA to get some trap doors or backdoors, but none of them are authenticated. Okay, so this is once again the operation. The half block is performed an expansion permutation, which increases to 48, and then you have the subkey of 48, perform an exclusive OR. The 48 bits are given as an input, get the 32 bits, rearrange them in the permutation, and you finally get the 32-bit output from the round function. Okay, now this is how the key generation. We have spoken about the entire structure of DES, the initial permutation followed by the 16 rounds, and then the inverse initial permutation, the 32-bit swap. Where do we get the 48-bit sub key for each round? As I told you, there are 16 rounds in total in DES. For each round uses a unique sub key. The problem with DES is we usually take a 64-bit key as an input. Out of the 64-bit key, only 56-bit key is only used. 8 keys are not used for the algorithm. The DES operates on the 64-bit blocks using key sizes of 56 bits. The keys are actually stored as being 64 bits long. This is a 64-bit key, but every 8th bit in the key is not used. That means 8, 16, 24, 32, 40, 48, 56, and 64 are not used. And these keys are subjected. That means out of the 64-bit key, we put it into a PC1, or we call it as a permuted choice 1. We call it as permuted choice 1, which selects 56-bit key from this 64-bit key. So we get, this is the order in which I get my 56-bit key. Okay. These 56-bit keys are now divided into 2 halves. So the 64-bit key is permuted according to the table PC1. This is a table. Only 56 bits of the original key appear in the permuted key and then divided into 2 halves. So out of 58, I divide into 2 halves, which is 28, 28. This produces an output of only 56 bits. Okay, we reduce the size from 64 to 56. And then you divide into 2 halves, 28 and 28. Once again, we have the left half and the right half. You can see that for each half, what I'm doing is I'm writing here an operation called as left shift. That means we shift the bits to the left. The two 28-bit quantities are then subjected to successive circular left shifts of different sizes before the subkey for each round is determined from them. What it means is there is another PC2 called as permuted choice 2, which accepts an input of 56 bits. That is the two 28-bit halves that you divided from the original key. And then it produces an output of 48 bits only. Okay. So how do you get these 28 bits? How do you get the different 28 bits for each and every round? For that purpose, for this left shift, it is not fixed. You don't fix the left shift here. What it means is for rounds 1, 2, 9, and 16, you can see 1, 2, 9, and 16, the left shift is done by only 1 bit. So this is left shift by 1, left shift by 1, left shift by 1, left shift by 1. So 1, 2, 9, and 16, the round numbers. For these rounds, the left shift is performed by 1 bit. And for all the remaining other rounds, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, the left shift is done by 2. So that is LS1 and LS2. There are 2 different left shifts. Please don't confuse yourself by thinking that left shift is fixed. No, it is fixed, but the different rounds will have different left shifts. Okay. The reason why is we need to get 48-bit unique keys for each and every round. Under no circumstances, the same key can be used for 2 different rounds. Once this is done, once the left shift is done on the 28 bits, these 2 28 bits are combined together to be as an input for the permuted choice 2, which will select only 48 bits according to this particular function. This is your PC2 table, permuted choice 2, which once again selects only 48 bits out of the 56 bits given as an input. So in this way, for the entire 16 rounds, we get different round keys for each and every round. So the PC2 selects the 48-bit subkey for each round from the 56-bit key schedule state. So this is how you produce 16 round keys of 48 bits each from the original 64-bit key. But do remember that the actual key size implemented for DES is only 56 bits. Though I am giving as an input of 64-bit key, the key strength of DES is limited to the 56-bit key only. Okay. Now, which brings me to the point where you define or where you discuss about the how good is DES. As I told you, it has been used prominently since the 1970s till the early 2000s. How good is this? Why most of the applications or most of the government agencies use DES? Because there are no apparent flaws with DES. And during that time, even brute force attack on DES is considered to be very complex and mostly impractical. If you want to talk about the strength of DES, any concerns regarding the level of security or any concerns about the security provided by DES falls into two major categories. The first category is its key size, its Achilles heel. The key size is only 56 bits. The second one is the algorithm itself, the structure of the algorithm, the way the algorithm works. In this, if you take the key size, earlier days in those 1970s and 1980s, it is considered to be good because 56 bits means it's a large enough key. But with current modern day supercomputers, it is very easy to break DES using a brute force attack. With a 56-bit key size, you only get 2 power 56 keys, which is equal to 7.2 into 10 power 16. Most modern day systems, given in recent studies, can work up to 10 power 13 encryptions per second, which is quite a huge number. And with that number, and if you want to break DES using a brute force, all this key size, all this entire key size material can be searched under an hour. So it takes less than an hour to break DES using a brute force search. That is the reason it faded out. Of course, if you just want to secure DES against a brute force attack only, you can increase the key size. That is the main idea where we have a new thing or where a new algorithm proposed using the same structure as DES called as triple DES, where we have 3 DES algorithms working in parallel, which increases the key size to 168 bits. And studies show that any algorithm which can have a key size upwards from 128 bits is generally cannot be broken off or cannot be attacked using the brute force method. That is the reason AES uses a key size of 128, starting from 128, 128, 192, and 256. Please do check out the video on AES also if you want to understand more about it. It differs from AES, DES in many ways. Though people think that AES and DES are two same standards, but no, AES algorithm is completely different. It does not follow the Faisal cipher structure, whereas DES follows the Faisal cipher structure, divides the data into 2 halves, and works on the operations on the 2 halves of the data that we just told you. So, as I told, brute force attack is a very common way of attacking DES. If you talk about the nature of the algorithm, cryptanalysis is also possible by exploiting the characteristics. There are 2 ways: differential characteristics and linear characteristics. Sorry, differential cryptanalysis and linear cryptanalysis are examples of ways through which you can attack the DES algorithm, the functionality of the algorithm. Most of the work on cryptanalysis on the DES algorithm is cornered around the S boxes, the design of the S boxes. Though there are some anomalies, but still today there is no proven algorithm or there is no proven attack vector which can invalidate the S boxes or which could discover the fatal weaknesses in DES. There is one other avenue called as timing attacks, which can be suitable for asymmetric key encryption algorithms like RSA or ECC. But what is a timing attack? A timing attack exploits the fact that an encryption or decryption algorithm often takes slightly different amounts of time on different inputs. There are studies which has proven that DES appears to be fairly resistant to a successful timing attack, and timing attacks are considered more successful for asymmetric encryption algorithms rather than symmetric encryption algorithms. So this is how DES works. My sincere suggestion for all of you is to please go through simplified DES algorithm where we work with examples, the same exact operations that we studied here, which makes you clearly understand the nuances of how the algorithm works, or where we are implementing the expansion permutation, or even the P4 or whatever these are, and also the subkey generation as well. So with that, thank you very much for watching, and do subscribe and share if you like the content. Thank you and good luck.